Hello and welcome to week 7 of ELEC50B. This week we're going to look at capacitors and capacitance. So this is going to be kind of the shift from a lot of theory, a lot of talking about stuff and kind of not seeing exactly how it turns out to now we're going to actually start building some circuits. And I know you've got a little bit of this already in the lab, as the labs got a little ahead of the lectures, but now we should be able to get everything caught up. So what we're going to look at this week is the characteristics of the capacitor, the different types, and then the calculation for the type, the total capacitance in a circuit. All right, so let's go to the next slide. Now, the term capacitance is really the ability to store electrons. And it will hold the electrons in the capacitor and then release them over time. Now, this is similar to a spring, right? A spring, you compress it and it holds that energy. And then when you release it, it will release that energy. So as it coils up and gets condensed, that's exactly what happens with the capacitor. All right, so let me something here. All right, so it's sometimes a capacitor is referred to as a accumulator or a condenser as well. All right, now the way a capacitor works is the electrons are stored in the capacitor for a given voltage, and it's measured in capacitance, and the unit is the farad, which is short for Michael Faraday, right, who kind of saw that properties of electronics and magnetism. Now, the capacitor's storage is basically limited to a time constant. And we'll get into that in chapter 21 with the time, with the transient time limits here. But the capacitor will hold a charge, and then eventually over time it will lose that charge. Because if you think of the capacitor as a bucket, it has a hole in the bucket, and it will lose, the electrons will dissipate or lose its charge over time. Right? Now, for now, we're only going to look at this from a DC standpoint. So just to get the basics. And then later on, we'll do the AC and capacitors, and you'll see where that you start having that time constant problem. All right? Now, when we looked at Chapter 3 way back in DC, we saw Coulomb's law, and we know that electrons are surrounded by electrostatic lines of force, and they're polarized from positive to negative, radiate from a charged particle in straight lines, have the ability to pass through any known material, and then have the ability to distort the orbits of tightly bound. So remember, with the magnetic or the electron orbits here, if two unlike charges are placed on opposite sides of an atom whose outermost valence electrons cannot escape, the orbits of electrons are distorted, right, because of the magnetism or the attraction. Now, a simple capacitor is the parallel plate capacitor, where there's two dielectric materials plates that are stacked on top of each other. So they're just laid on top, and then the conductors can move in between them. And the dielectric material used must be a poor conductor or an insulator. Okay, so here's the plates, and then here's the dielectric, the insulator in between them, and then the charge will want to move from one plate to the other because of the magnetism. Okay, so here's some theory on this. This is all out of the textbook, chapter 20, so you can read that. But when the capacitor, when that electron moves all the way across and it's fully charged, the potential of the capacitor and the source are equal, means they're in opposition. So if we have a simple capacitive circuit with a 10 volt battery here and a capacitor here, if we close this switch, boom, so it's over here, after a certain amount of time, this is negative and positive here, and then it's negative and positive there. So it's going to be 10 volts in the opposite direction. So it's going to oppose it. Okay? Now, if this, so that's a common thing with the capacitor. Now the symbol, you can have the normal capacitor, or which is either two straight lines or straight line, curved line. If it's an electrolytic capacitor, which means it's charged, it has a polarity, you'll show that the straight end is going to be the positive and the curved is the negative side. And then if it's a variable capacitance, it will have the arrow through it. Okay? Now, one of the formulas here, to calculate the capacitance, you take the charge in coulombs divided by the voltage. Okay? And you can calculate that. So 1 farad equals 1 coulomb over 1 volt. So here, 1 farad would equal 1 coulomb over 1 volt. And there's some calculations here. We're not going to get into a whole lot of that. But we can use this formula to calculate the amount of capacitance when 50 microcoulombs of charge is deposited on the plates and raises potential difference to 2 volts. So to do that, you just do C equals Q over V is 50 times 10 to the negative 6 divided by 2 volts, and you end up with 25 microfarads, or 25 times 10 to the negative 6. All right, so in this week's homework, there's I think I have one problem where you'll do something similar to that. All right, and then here's another phase on that says a constant current of 4 milliamps charges a 10 microfarad capacitor in 1 second. How much current is across the capacitor? So now the formula is Q equals the current times time. So that gives us the coulombs, and then we divide that by the capacitance, and it will give us 400 volts. Right? So some just basic formulas here. Right? So here's another formula or another problem that's in the textbook. You can work on those in your own time. All right? Now, there's 3 factors that the capacitor depends on. One is the size of the plates, or the area, and then the space in between the plates, and then what the dielectric material is made of. So the greater the area, the more charge the capacitor can hold. The closer the plates, the stronger the force is between them. And then depending on the material, that can also have a factor. And there's a formula here where you can calculate this and so forth. Now, at higher voltage, certain dielectric materials will break down, which will cause them to arc across the capacitor. So I don't know if any of you've ever had a video card in your computer that has a blown capacitor, and you can normally tell because the end of the capacitor will be all puffed up. So instead of being flat, say this is circular and flat, or here I'll hold my coffee cup here, so the top of it is flat, it'll be puffed over. It'll have like a bump where it explodes or pops over and it fails. And that's common on some of the older video cards. You'd have that all the time. Okay, some TVs, if they won't turn on or off, or like a TV, my brother-in-law had a Samsung TV, you'd power it on and then it'd power off right away, and you hear a click. Power it on, power off. And I took it apart. Inside there were like 6 capacitors that were all puffed up. I desoldered them, got the values, ordered them, actually got them for really cheap. They came from China. Put them back in, the TV turned on, and the screen was all smashed up. It had a bunch of broken fragments on it. So I called my brother-in-law. I said, hey, what else? What happened to that TV? You said it wouldn't turn on. He goes, yeah, it didn't turn on. I got mad and I threw it. And I was like, well, I wish you had told me that before I spent all this time to replace the capacitors. So that I fixed the problem with it not turning on, but now the screen is all broken. So it was still no good. All right. Now, with capacitors, they can either be variable or fixed, right? So a fixed capacitor it has one capacitance, right? It's rated. So if you look in your parts kit, and you've done this in the lab already where you build a little circuit, that capacitor will have a fixed value. Variable ones can be changed, right? You can rotate them just like a rheostat or a variable resistor where you can change its value like you did in DC. Same thing here. All right. Now here's kind of the form factors or the packages that they come in. This one's very common. This one's very common. And then the ones we use in the lab are most of them look like this. All right. So you'll see that as you work with this. Now, one of the first materials used was mica, which is like a silicon. Formica is a form of mica. And different capacitors, you can have paper-filled ones, you can have ceramic, and so forth. All right? And then there's normally a plastic film that go around the capacitors to neutralize it. And here's some more details on how they make the capacitor, right? They have the foil and the variable, and then they wrap it up, and then the charged ones go in between those through the dielectric material in between. All right, here's another capacitor. Here's some other things here. Now, capacitors may be marked to show their value, voltage rating, and tolerance temperature. And the value is always specified in either microfarads or picofarads. Now remember, micro is 10 to the negative 6. Pico is 10 to the negative 9th. Now whole numbers are normally picofarads, while a decimal fraction is a microfarad. All right? Now another version may have a 3-digit coding system. And the first 2 digits of the code represent the significant digits, and the third is the multiplier. And a letter would indicate tolerance. So if the first digit is a 1, second digit is a 1, and then the third digit is a 1, that means it's 1 times 10, so that's 10 microfarads. All right. All right. So for this capacitor, if you wanted to determine its value, you'd look at this number here, and the solution for the first one is 102 equals 10 times 100 picofarads. So that's 1,000 picofarads, which would be 0.001 microfarads. And then they're like that. All right. And then when they're surface mounted, they're going to have different labeling here. All right. So now let's get into some of the circuit analysis. And with capacitors, think of capacitors as the opposite of resistors, right? So like we know in a series circuit, if I have resistor, and so forth, and this is R1, R2, R3, R4. In a series resistance circuits, RT just equals the sum of R1 plus R2 plus R3 plus R4, right? So you just add them all up for series. And then when they're in parallel, you take 1 over R1 plus 1 over R2 plus 1 over R3, and then take the reciprocal of the whole thing, and it goes from there. Now in capacitors, it's the opposite. So capacitors in series are the same as resistors in parallel. And then capacitors in parallel are similar to resistors in series. So they're opposite. So here's the formula for series capacitance. So to find that, if you were to say, what is the capacitance of a series capacitor? You would just take 1 over 1.01 times 10 to the negative 6 plus 1 over 0.25 times 10 to the, and so forth, and you would calculate that and then take the reciprocal of all of that, and you'd end up with 0.08 capacitors. Now notice your smallest capacitor is, this is 10 picofarads, right? That's 50,000 picofarads, which would be 50 microfarads. So, or no, 0.05 microfarads. So a pico is 10 to the negative 12th. I said 10 to the negative 9th earlier. That's a nano. But so you would take these values, and you're only going to be as small as or you're going to be just under your smallest capacitor. Just like series or resistors in parallel, your total resistance is always going to be less than, just barely less than your largest resistor. So that's what this is here. All right. So you can see how that's calculated, and then capacitors in parallel are just, you just add them up. So you would just take C1 plus C2 plus C3 and then add it up. So here, if you have 3 capacitors whose values are 0.03, 2.0, and 0.25, you would just add those up and you get 2.28 microfarads. And then if they're in a combination circuit, so let's say we have a voltage, so let's say we have our voltage source here, and then we have a capacitor, and then it comes down here, and we have a capacitor. That's a capacitor, not a resistor. And it comes back. So here we have a series parallel circuit. So what you would probably want to do is just add these two up and then replace it where it's just in a simple series, and then you would get your CT here, which would be 1 over this capacitor plus 1 over this capacitor plus 1 over this capacitor. Add that up and then take the reciprocal of it, and you get the total capacitance. All right? So there's a problem in the homework where there's 1 series capacitance, 1 parallel capacitance, and then 1 combination, right? So you can see those when you do that. All right, and that's really the majority of what I want to cover to get you ready for the homework anyway, is what we just covered there. And there's some other stuff in this chapter that you can go ahead and read through to get a good feel for it. And there's some straight capacitance, troubleshooting capacitors. Now, the most common faults are either short and open or one that leaks too soon. Shorts and opens can be checked with an ohm meter, and caution must be taken to ensure the capacitor under test has been discharged. So again, I teach in the CNET department, all right, the CNET program. So a lot of my examples are going to be computer based. One of the things we talk about in computer repair is when you start to work on the motherboard, you always want to pull the power from the computer, then press and hold the power button to dissipate all of that stored capacitance that might be in the power supply. And then the same thing is true when you work on the video card. When you take it out, you want to let it sit for at least 10-15 seconds so that any of that capacitive charge will dissipate. If you take a meter, if you were to take a capacitor and charge it up and then remove it and then take a meter, you would see a huge spike of voltage. So it would go way up. And in fact, let me show you something real quick. So here is a thing that was common in computing for a while, which was known as a USB killer. So it's a drive that's been modified to deliver a huge electrical surge that can damage or destroy hardware. So what they do is they basically modified the drive with a bunch of capacitors that rapidly charge and discharge repeatedly. And what they would do is take these drives, these little USB drives, and drop them in the parking lot of, say, their competitor. Say we make a product and we have a competitor who makes the same product, kind of a form of, competition. We could go out in their parking lot and just take some of these USB killers, throw them on the ground, and then people would, they'd say, oh, someone left their USB drive. Let me take it and plug it in my computer and see what's on it. And while they did that, they would see that it would deliver 210 to 220 volts to an interface that's designed for 5 volts, right? USB uses DC 5 volts. And it would just cause the computer to blow up. So let me see if I can find a YouTube video here. If you search for USB killer, and yeah, I don't think they have one that actually shows it, but here's versus PS4 and Xbox One. So it's just, you can, anything that is designed for good can be used for bad, right? Now, a good capacitor should indicate near 0 ohms, right? It should have continuity. As the battery in the ohm meter charges the capacitor, the ohmic value should move forward towards infinity. So remember, our meters, when it's in resistance, is providing a voltage. And then it divides by the current and calculates the resistance. And when you plug that in at the beginning, the capacitor will be 0 ohms, and then it will slowly go up to infinity when the battery in the meter actually charges it. All right, so you can see that there. Now, the short indicates lower 0 ohms, and this can be caused by a rupture of the dielectric or when the plates touch. And open is often caused by damage to the dielectric, and this will show very high or infinite resistance or ohms. Now, some capacitors, they age, they leak due to deterioration of the material. So a puffed capacitor, let me see if I can find a good image for that, because you might see this. Yeah, so like here's a capacitor where you can see the top here has puffed up, right? These plates, if you take your finger and just run it over the top of that, you'll feel there's like sharp edges where those 4 plates pop up, and you can feel that, and that tells you that capacitor has damage. So here's another one where it shows where they marked them. These 3 are bad. This one is still good. Okay, and here's some more, and you can just tell, right? They're puffy. They should be flat. So when that material gets, when it gets overcharged, it's going to pop up. All right. So let me see here, where are we at? And that's it for this chapter. And again, remember also this week, when you go to lab, you'll pick up the take-home test. So test 1 is take-home. It's 100 points. I think there's 45 different questions on there. And just look at how the points are matched up. And make sure you complete that, and then you're going to turn it in at the start of week 8's lab. There's also a homework. The homework is really light this week. I made it just 5 problems and 2 points each. That shouldn't take you a long time, and that's related to chapter 20. The test 1 is covering chapter 14 through 19. All right? Well, let me know if you have any questions, and I'll see you online.